Thank you, Ricky. Thank you, WoodWorks, and thanks for asking me to come here and tell you a little bit about what I've learned over the last couple of years working on wood-on-wood composite action. I want to thank the Forest Business Network for organizing this great conference, especially the building tours. I've been here for 3 years for all 3 of the conferences, and I've learned so much, especially on the tours, but also strengthening knowledge and connections to friends that I now have around the globe. It's a pretty cool community we have here. And so I want to thank you guys all for being here too. I know it takes a big effort to take a week off from work and go work in your hotel at night or whatever. So thanks for coming together and propelling our mission forward. So the first thing I want to talk to you about is just to spend a few moments. This isn't quite working. Got to turn it on first. Okay, that works. Spend a few moments just reviewing structural mechanics. I'm not a professor or anything, so I'll try to make this brief, but specifically there are bending moments and shear forces that get applied, or that when you apply load to a beam get created. Most people get the bending part kind of intuitively. You know, the top compresses and the bottom stretches, so you get compression and tension. But in order for those forces to work effectively together under load, the beam must carry some shear forces. And it's, shear is kind of where people, it's one of those magic words that engineers say and architects' eyes glaze over, because shear goes this way and this way and this way. And so it's a thing that some people get tripped up on, but the math is actually pretty interesting if you're a math nerd. That moment, let's see if I write this down because I often misspeak, but shear is proportional to the integral of the load, or the weight that's on the beam, and the moment is proportional to the integral of the shear. They're both further related through differential equations here to slope and deflection of a loaded member. So these are kind of the 4 equations that engineers solve, or their computer programs solve, in order to figure out what the moment is and the shear is at any point along a beam. But the shear stress within a beam is a different thing. I mean, the shear force is, it's the same shear that gets applied to the top of the beam, but the shear stress is the sliding force between, or the sliding between the theoretical infinitely thin laminations of a beam. The shear stress equation turns out it's the shear force times the first moment of area divided by the second moment of inertia times the width of the beam. And for a rectangular beam of uniform material and uniform section, rectangular, like most timber beams, it turns out that the max shear stress is 3/2 B over A. That's right down there at the bottom. And that happens at the middle of the beam, and it tapers parabolically off to 0 at the top and the bottom of the beam. And sort of intuitively, that makes sense because nobody's pushing on the top or the bottom of the beam. It's all the internal forces that are pushing against each other. So you just took a college mechanics course in 3 slides, and one of them had a sheep on it. So I'm going to show you a shear stress diagram in a minute or two to illustrate what I've been talking about, but I need to give you a little bit of context. So at Bensonwood, we just got a new automated wall panel and roof panel building machine here. It's a Wyman. And we're pretty excited to drop our labor costs with this panelized equipment. Our sister company, Unity Homes, has been building high-performance houses for the last 5 years, all by hand in our factory. And we've really struggled to compete with our own insulated roof panels versus an insulated stick gable truss. So a lumber truss, insulated flat ceiling versus an insulated set of roof panels. And one of the reasons is labor, that, and we think that equation is going to change. But the other reason is that the roof panels need a ridge beam to prop them up. So for us, Bensonwood, we're a lot of timber framers, and the costs of our timber frames aren't exactly nothing. So we wanted to look at using this equipment to build a box beam ridge beam that would span like 36 or 48 feet, kind of clear span the whole volume and let our roof panels land on top. And so the engineering department looked at it for a little bit, and we're getting into, okay, what type of nails do we need, how close they need to be, what size the cords at the top and the bottom, And we realized that the equipment we bought at auction out of a company in Canada, they don't quite use big enough nails up there, so we would have had to tool up for new nail guns and everything. So one of the drafters just said, why don't we just use a built-up pack of lumber girder of girder trusses. So it's kind of ironic that that's the solution we're going, because we're using lumber trusses so that we can do our panels, but that's where we are in testing now. But anyway, this diagram here, you can see sort of high shear stress. The little dots are red there. The blue is kind of no shear stress. So the shear accumulates, and there it is at the neutral axis, or along the center line. In this case, it was where the sheathing seam was. But you guys came here for timber, so I got to really change the topic back to timber. And my story with timber starts in 2001. When I was a graduate student at MIT. My first day of classes was September 11th. And I was there at MIT on a research scholarship funded by British Petroleum, who at that time was building a new green building in Aberdeen, Scotland, to exploit the North Sea oil fields. So after September 11th, kind of the irony of my scholarship wasn't lost on me. And I did a fair amount of soul searching, and I came from northern New Jersey, right outside the city, so it felt like a personal attack. And I decided that I didn't want to study energy. I wanted to study resources, because I felt like a lot of the global conflicts are based in resources. Even before it's about energy, it's about resource. So I changed my focus to natural materials, biomaterials, and I got really into straw and timber and bamboo. And when it came time for my summer away from MIT, I got a job. My advisor was, he knew about Bensonwood, and he had some personal connections. So he got me a job in the timber frame shop that summer. We had two big jobs that summer. One of them was the Tewksbury Country Club in Tewksbury, Mass., and the other one was this building, Stratton Mountain Club in Stratton, Vermont. And they both used keyed beams, or what we were calling keyed beams. So you can see here we got 3 stacks of Doug fir with hardwood cherry keys. The posts were keyed as well, because the braces induce a bending moment on the posts. So these keys were just really cool, and because they're both kind of big jobs for Bensonwood, I spent the whole summer looking at them on the floor, and to me, Douglas fir and cherry, they're just beautiful, and so I was kind of enthralled with them. And though I spent most of my time sweeping the floor and kind of messing up the housings by tapping poorly, they did let me go out on site for the last 2 weeks and help the crew put that building up. So when I came back to Bensonwood the next year and started in the engineering department, I kind of wanted to learn more about keys, and we were still doing them at the time quite a bit. And at that time, it was Ben Brungraver leading the engineering team with Duncan McElroy, Annette Dye, and myself. So we had a team of 4, and we took on interns, a lot of them from Europe, from places like Biel, where Matthias Oberholzer came from. And he was there in 2005 and helped us, with Annette's help, translate the DIN and put some of these slides together. But basically, with shear keys, you space them according to the shear in the beam. So the integral of this triangle is, or the area of that triangle is equal to the area of that triangle. And each one of those areas sum up to a shear force that the key handles and prevents the members from slipping by themselves. And this can be done graphically as well, with a protractor or a compass and some rulers. And these are slides that Matthias made for us just to help talk about it and show people how to do it. We also made a spreadsheet, so thank you for him to help us figure out where keys goes, just to follow shear flow. But it kind of all boils down to strength and stiffness. And the strength part, that's that spreadsheet. The stiffness part is actually a little bit more complicated. And it comes down to this gamma factor here, which is somewhere between 0 and 1. If it's 0, the 2 beams might as well just be side by side with each other, not working compositely at all. If it's 1, they're theoretically fully fused. And so with keyed beams, we're thinking we're in the 0.6 area, maybe a little bit higher. I'll let Max and Flavio tell you about maybe what it is for screws. But the keys, let's see. So the keys prevent sliding action, and their orientation of the hardwood keys makes a difference, because the fibers can intermesh when you have bearing on end grain, or the fibers can roll in the shear key themselves when they're trying to slide by each other. You also wind up with the difficulty is getting them all to fit really tightly. So that's a lot of the reason why sometimes we'll use these tapered keys and push them together so that you guarantee that you get tight fit joints and stiff performance. There's always, I should just mention, there's always a clamping mechanism, whether it's a clamping band or some screws or bolts or some manner to keep that key from rotationally moving. Through cogging action is how the keys work. And none of this is new. 1726, and I'm sorry about the quality of this slide, but Jacob Leopold, German mechanic and instrument builder, put this diagram out. I'm going to jump ahead to 1897 when Edgar Kidwell, who's an American engineer in the copper mining industry and also a professor at Michigan College of Mines, did full-scale testing on these keys and wrote all about a number of different configurations and what you can do, and published a journal article called The Efficiency of Built-Up Wooden Beams. Interestingly enough, in 2003, Joe Miller got his PhD at Michigan State, basically did a lot of the same research, performed a lot of the same tests, and came to a lot of the same conclusions. So, the physics hasn't changed in over 100 years. It's just about things sliding by each other and how do you prevent that from happening. In 1820, about 80 years earlier than Kidwell, Thomas Treadgold, who was a British railway engineer, advocated for this type of keyed beam where they joggled the two beam surfaces and got the bearing surfaces to hit here. And then they used this cast iron, call it a keystone, to induce compression outward in the upper lamination, tensioning the bottom lamination. So, well, this idea isn't necessarily new because Leopold had suggested something similar. It's a pretty bad idea. Each one of those laminations' effective depth is reduced just inherently by making that sawtooth. So the potential of the built-up beam is automatically a lot less because, what is it? Strength is a squared factor of the height of the beam. So, and back then, there's no way you're going to get all of these faces to line up perfectly. And if you start inducing a big amount of compression here, the tension here is going to maybe pop the beam apart. So, well, maybe not a good idea. I kind of thought it was a cool idea. Well, the proportions of this got really messed up there. Maybe the next one's good. No? So the story here is Christine Benson, Ted's wife, her oldest horse passed away a couple years ago, and they decided that a better lifestyle choice than horseback riding was bike riding. So they decided to take down their fence pasture and turn all these locust pieces that they had into a woodshed for some firewood that they use. So we assembled some other pieces of locust. We got some Doug fir beams for the eave plates, and we made everything we could keyed in this job. And they were all sloped and tapered. The tension ties here between the eave plates had splines in them that were keyed through the member, but the splines themselves were also a key between the two plates. And we even did put a keystone in there as a homage to Treadgold. Maybe not a good idea, but we analyzed the beam with the effective depth or the effective cross section, losing the hole. So felt pretty good about it. And it's pretty nice. But you're here at the Mass Timber Conference, right? So I should tell you a little bit about Mass Timber and some of the projects we've done with that. So this is the Common Ground High School under construction in New Haven, Connecticut. We did with Grayer Gansky. And the north end of the building, that's this end over here, that has these 66-foot long clear span trusses that hold up roof panels. The roof came up. This is the clerestory, comes down. Right at this member, you'll see this member in a bit, jumps back up. And then from here to the south end of the building, the roof panel here was pretty interesting. So just remember north and south as I get through this. So the finished picture of it. The south end of the building is a two-story space with classrooms, art classrooms up high, art and science classrooms. And it had this really nice glulam CLT composite stringer You can't even see the screws here, but there are screws from underneath connecting into a sawtooth stringer, and the guardrail was connected as well. So this all works compositely. Actually, if you look really close, you can see some screws up here, and that's because the spacing gets tighter up where the shear is higher in the beam. So when you get up to the second floor at the top of the stairs, the roof panel here is a CLT box beam roof panel, insulated box beam. And they're 8 feet wide. You can see the innies where the two panels come together. And we just rabbited a little dado at the edge of each panel and put a piece of trim in there. And what we were able to do there was connect the vapor barrier and hide it in the end. So it was pretty important for vapor tightness to get that right. But this was a composite box beam panel. The CLT was working in tension, spanning about 30 feet there. The I-joist and the top skin, the OSB sheathing, was Advantech, or Zip, I should say, was working in compression. And we looked at this, and the joists themselves, or the purlins themselves, were pretty much strong enough to go the distance, but it was about stiffness and about getting more for something that we were already building. We wanted the CLT, the exposed wood in the ceiling. We wanted the high performance, so we had a deep joist for insulation purposes, and we wanted the weather protection of the Huber Zip. So this is how it happened. Nordique CNC'd all of the electrical openings and sent us the panels, and we stood them up in our shop. It was like working in the canyons. The electricians came and loved working on their feet, wiring a ceiling. And then we were able to put that vapor control layer in that I was telling you about. After that vapor control layer went in, we did the I-purlins, and you can see all these little screws, boom, 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 boom. And it's hard to see with the perspective, but they're tighter towards the end than towards the middle. So we had to figure out, what is the shear slip or the shear force between all of those layers, and what do the fasteners need to be in order to handle that force. So in the CLT handbook, there's some equations that you can go through to figure out where the neutral axis is and then what the force is between each layer. And in the end, it kind of for everything, it all boiled down to this detail here where there's your screw spacing, and that's the center line of the beam, and you can see as you get out towards the edge, you need more screws, just like you needed more keys. So it was all going together pretty good on site. For something this complicated geometrically to go together is a challenge, and we were feeling pretty good about ourselves until I got a call from the site. And we had talked about it before they went. We thought maybe there'd be a 1/4 inch, 1/2 inch of dead load deflection. And so when they set this last panel here over this big opening, they noticed a 3/4 inch deflection, or a 3/4 inch difference between these two panels. And they weren't sure what was going on. And in the engineering team, we got kind of excited about it because we didn't know what was going on. So we started scratching our heads and said, well, what could have happened? What could have? So we walked around, and eventually we figured out that the pre-drills that we had put into the computer, little axes in our CAD model, and specified as 1/8 inch diameter, the 1/8 inch drill bit didn't get in the machine that day or that week, and they left the 1/4 inch bit in the machine. And of course, with a 1/4 inch shank, you'd never want to drill anything bigger than like 0.6D. So the 1/8 would have been okay, but the 1/4 inch shank, and it's actually a little bit less than a 1/4, wound up being about a 1/16 of slop of sort of intentional or unintentional, but effective slip between those layers. And holding the centerline geometries and letting those two things slip by a 1/16 of an inch, it turned out there was about a 3/4 inch deflection before the screws could engage. So we're like, well, that actually makes some sense. But sense is one thing, and feeling like you actually know that the things aren't going to continue to go bad is another thing. So me and the project manager went down and filled up a kiddie pool and drank a martini in the pool and jumped up and down on the roof and set up a laser underneath. And actually, he couldn't measure any more deflection, even after the pool was stood up and I was jumping up and down. So by the end of that, given that the purlins were strong enough and we weren't measuring any more deflection, we felt like we knew what was going on and everybody's going to be okay. And in the end, it looks like the kids are okay to me. So at the north end of the building, we had this like I was saying before, this 66-foot long truss, and then a set of roof panels that went down to here, and then another set that jumped up here. And the ones here were purlin framed, and the ones here were rafter framed. And you can see the shear stress developing out in these edge panels and along the seams there, just like you saw it before. And so we had to get very specific about those panels. What our panels are normally built out of are 1/2" or 5/8 skins of OSB with nails. Here we're using 1/4" screws and 1 1/8" skins of OSB. And it was pretty burly, I guess is the word, to watch these guys run these screws in. So they all got stitched together to this continuous skinny 6x10 that was 66 feet long with the screws. And I do want to jump over and show you a video. Yep, I've got 5 minutes. So this is, just because, you know, I like fun things. This is that, oh, hold on. Yeah, I got to drag it over. You just don't get to see spaghetti that much.
Okay, let's watch it wiggle.
Change the frequency.
That's Philip Henry. He spent 5 weeks putting that building together on site.
Okay, let's watch it wiggle.
Excuse me.
Change the frequency.
You're going to hear me say watch it wiggle like 4 times. Yeah, okay. In the end, that beam is completely hidden. There's a mechanical triangular zone right up in here that was super important for the mechanical engineers. But you know, the thing I love about the project is the architect and the owner are unabashed about, you know, exposing structure, including this big exterior wood bridge, and it really fosters collaboration among the students. There's all these little spaces where students can gather and learn about structure and learn about the building and learn about each other, and it's an environmental charter school. So these are the students that, you know, are important to teach for the future. So it's almost a metaphor. Composite action is like a metaphor for collaboration, in my opinion. And given that, I want to just give a shout out for the Timber Frame Engineering Council, of which I'm a member. We're a group of timber frame engineers dedicated to improving ourselves in the craft of timber framing. We primarily serve ourselves and the Timber Framers Guild by writing articles in guild presentations or guild publications, making information available for download, and sponsoring workshops and seminars, including wood identification, timber grading courses. Membership is inexpensive, and there are group rates, so an entire office can really sign up very affordably. I encourage anybody to join. You don't need to be an engineer to join, so we can all collaborate, debate, and give back to our industry together. And I've seen this sort of collaboration and spirit in the mass timber movement as well. These are my kids down at the National Building Museum at the exhibit that Yugon Kim curated, and I helped engineer. It was fun to see the Common Ground High School model show up down there. And it was also fun to help D.R. Johnson and Structurlam figure out, you know, how to hang these panels inside the building. This was a lot easier than carrying a 60-foot long timber inside the building. So there's some fun details there. And DR and SmartLam and all the North American CLT manufacturers, you know, they donated their time and their energy to this program to educate the leaders of our country and the future leaders of our country. And that's just really important. At the heart of the Guild is a spirit of fun and a spirit of community. And it's just important to think of composite action is so much a metaphor for you get stronger when you work together. So in that way, you know, let us work together. Let these 12 guys make a nice 12 lam and help serve the industry and bring us to the next level. So thank you. Thank you very much.